You'll often find analogies of quarks involve Lego, and there are many good reasons for doing this. Lego is pretty indestructible. You can't really get any smaller parts than your Lego blocks. They also can be used to build structures, and they can be distinguished. So you could, for example, say that a yellow block represents an up quark and a blue block represents a down quark. So if I have an up and two down quarks, then I might be representing a neutron here. If I have two up quarks and a down quark, here we go, I'm representing my proton. You could maybe even add little labels to the each one, just using an indelible pen, for example, and show that some of the rules like baryon number, like charge and so on, all end up being a combination of a whole number. However, there is a complication, and that is that we already have allocated colours to quarks. Effectively, the colours of quarks really represent a direction in space, and we really don't want to go into the details, only to say that this is one of these rules that makes only some combinations allowed. So you could well have a student who's read about quarks, or you may read material about quarks that talks about the colours. And what we're trying to say is all quarks have to be colourless. In other words, we actually have to have a combination of a blue, green and red. And this is more to do with the orientation of the quark than actually a fundamental property of the quark. Similarly, if we have a meson and we have a quark and an antiquark, then in fact the directions of the arrows cancel each other, or the colours cancel each other. So that's a complication. We're already using colour to represent not colour in quarks, and now we've got colour in our Lego not representing colour in our quarks. You may find some demonstrations, so I think the UCL demonstration, no, it's the KCL demonstrations, which I think are very good, will build all their quarks just using 3 combinations of colours. They will all be using red, green and blue, and then they might say, well, this one is a neutron and this one's a proton, but it's actually very hard to tell that that's actually what's going on. And they've done that because they are representing colour, which we don't need to cover at A level. I might personally be quite happy to say, well, if I've got a quark and an antiquark, here's a black and a white, I'd sort of say those are almost anti-colours, but it is quite hard for me to show anything else with this. So Lego, it's fine, but it's very limited use in many ways, because it could actually add to some of the confusions.